A structural analysis of Chevrolet Avenue Bridge. The goal of this project is to apply what we have learned in this course about material mechanics to a bridge under load. We chose the Chevrolet Avenue Bridge because it's straight and flat, which brings our simplified model closer to a real-world representation. We came up with a maximum theoretical load case and calculated the stresses it would experience.
Interestingly, this bridge was near GM's Fisher Body plant and was the scene of a sit-down labor strike in the 1930s. Later, in 2006, the bridge was demolished and reconstructed because it no longer met structural safety requirements. Once surrounded by GM factories, the bridge has since become a feature of Kettering's campus landscape.
Moving on, the bridge is symmetric about an expansion joint at its center, so we considered just one half of the bridge. From there, we modeled it as a simply supported beam. The real bridge uses box girder construction, but we simplified this to a solid rectangular cross-section. We also assumed that the bridge was made of a homogeneous material, consisting of 97% concrete and 3% rebar. These assumptions guided our analysis of the bridge's strength.
One might choose heavy traffic or crowds of people to test a bridge, but we decided to consider how our bridge would handle civil unrest in Flint. We fit 6 M1A2 Abrams tanks on the bridge, a total mass of 352 metric tons. The M1A2 is the workhorse of the United States military, and in the event of a civil war, they will undoubtedly be deployed. Tanks are extremely heavy for their size, so this scenario really puts the bridge to the test. To calculate the weight on the bridge, we considered the weights of the deck, the tanks, the sidewalk, and the railing. Here is our static analysis of the bridge for this loading.
Next, we use Maple to parametrically analyze the structural reactions of wartime loading along the length of the bridge. Beginning with the expressions for bending moment and normal stress on the bottom face, we found the factor of safety to be minimum at the center of the bridge. Then we found shear force and shear stress along the middle face, yielding a minimum factor of safety at the endpoints of the structure. Comparing the factor of safety for shear and normal stresses, we saw that the overall factor of safety was dominated by normal stress over the majority of the bridge, with a minimum value of 2.97. This indicates that the bridge is stronger in shear than in tension.
According to our simplified model, Chevrolet Avenue Bridge is most likely to fracture at the center of the bottom face if it was subjected to load in excess of its strength. In addition, the bridge should be strong enough to withstand the 6 Abrams tanks with a factor of safety of 2.97. That said, our model doesn't come without limitations. It is possible that the bridge is weaker than we estimated, as our solid block model ignores the hollow areas present in a box girder design. It is also possible that the bridge is stronger than we estimated, as we ignored the steel beams and pre-stressing of the concrete. To more accurately model this bridge's mechanical performance, one must account for the box girder cross-section, the use of non-homogeneous materials, and the compressive stress offset due to its pre-stressed construction.
Here are the resources we used during our research. Thanks for watching. We love you, Professor Tari.